Hello friends, welcome you all in this course on fundamental of engineering physics, and today I am going to deliver a lecture on one new topic, that is Heisenberg's uncertainty principle, and this is a very special topic because this actually creates the difference between that the classical physics, means Newtonian physics, with the quantum physics. So, in this lecture we are going to learn about some fundamentals to understand this Heisenberg's uncertainty relation, Heisenberg's uncertainty principle, and those will be covered as background of this because in one of the lecture we have discussed about that the wave nature of particle and particle nature of wave. So, here we will use one of that is that the wave nature of particle, that is known as the matter wave. So, some glimpse on that the concept of that matter wave and some relevant property to understand or to this particular principle, because this principle is actually related to that the position and momentum type parameters of that quantum mechanical particles. So, that will be considered as the background of this. Then we will move to learn about this Heisenberg's uncertainty principle, what is actually this, and then some uncertainty relation. So, the principle it is that theoretical statement, and the relation some mathematical formulation, and then some thought experiment in the support of this uncertainty relation, and then this Heisenberg's uncertainty relation with some applications, good applications of this, and then finally, I will summarize as a conclusion of this talk. So, objectives of this lecture is to introduce Heisenberg's uncertainty principle and to impart knowledge on the uncertainty relations, and to introduce some thought experiment in the support of this uncertainty relation, and to give different applications of this Heisenberg's uncertainty principle. So, outcome of this lecture. So, after attending this topic, the learner will enable to understand the basic concepts of quantum physics concerned with this uncertainty principle, and apply this uncertainty relation to understand various complex physical phenomena, because this relation is already complex. So, this actually predict or explain some contradictory phenomena or complex phenomena, and they will be able to learn some fundamental mathematical formula to solve properties of the quantum levels. So, first of all, let us overview on that the wave nature of a particle, that is known as matter wave. Earlier we have mentioned in the detail in one of the lecture that we know that the moving body behaves in a certain way as through it has a wave nature, and the de Broglie in year 1924 proposed that the moving objects have wave as well as particle characteristics, means that dual nature of light, it is not limited to light. The dual nature is common for all the objects which are in motion, and the existence of de Broglie wave, these are known as matter wave. This was experimentally demonstrated by 1927 by Davis and Germer, two group of scientists, Davis and Germer, and J.P. Thomson, the son of J.J. Thomson, and that duality principle provides the starting point of the Schrodinger's successful development of quantum mechanics. So, this is one of the milestone in the development of that quantum physics, this dual nature of matter, that is the matter wave. We know about that the momentum of photons, that is this is that bridge equation P is equivalent to h upon lambda, and here this P is the momentum that actually give the particle nature of the particle characteristics of that particle, as well as that h upon lambda. So, lambda is the characteristic of wave. So, one can consider this as a bridge equation, and de Broglie used this relation and that rearranged it for lambda and give one expression for the wavelength of matter wave. So, which is equivalent to lambda is equivalent to h upon p. So, p is here the momentum, and one can generalize this momentum p from that energy momentum relation from Newtonian physics, that p is equivalent to root of 2 m e k, and by putting this value, that generalized equation is equivalent to lambda is equivalent to h upon root 2 m e k, where e k is the kinetic energy. So, if we have different types of material depending on its state, for example, if it is bulk material, mechanical body, or charged particles or gas molecules, depending on this type the nature of this, we will have different formula for the de Broglie's wavelength, the wavelength of matter wave as lambda is equivalent to h upon root of 2 m cube v. This is for the charged particle moving in particular potential difference, constant potential difference v. And next is when we put one, we consider that gas molecule which is moving in a constant temperature, and that is that relation that lambda is equivalent to h upon root of 3 m k t, where k is Boltzmann constant. So, experimentally it was proved that matter wave exists. So, if this matter wave exists, then there must have some more properties of this matter wave we must know. With as we know that the transverse wave or that mechanical wave or other types of wave, where we have that different wave equation, wave function, velocity. So, for the matter wave we also should have these properties. So, what is this matter wave? This is actually known as the wave of probability, because if we think about that water wave, then the quantity that varies periodically is the height of this water surface, and in sound wave it is the pressure, in light wave the electric and magnetic fields, that variation, that flow, and what is that varies in case of this matter wave actually. So, this quantity which variation makes up matter wave is called the wave function psi. So, this psi, this is the Greek word, and first time this wave function psi, it is used by Max Born, and this value of this wave function associated with this moving body at a particular point, that position x, y, z in the space of time t, it is related to likelihood of finding the body there at time. So, this wave function psi, this is a wave function which is used to represent this matter wave mathematically. So, a list of that different properties of this wave function psi, that was given interpreted by Max Born in 1926, and he has given that list of properties of this wave function psi. It is a complex quantity, it is a finite single valued, it is a derivatives, that wave function psi, and it is a derivative del psi by del x, del psi by del y, del psi by del z. These derivatives are continuous function. So, these are some mathematical terms, because basically this Max Born, this was a mathematician. So, he has given lots of mathematics to interpret this, and this one thing, this wave function psi, it itself has no any direct physical significance. The reason is simple, because this wave function psi is a complex quantity. There is that imaginary part there. If we represent this psi, then this psi is equivalent to x plus iota y. So, this iota term is there, this is imaginary quantity, that is why we cannot directly interpret physics by using this. So, what we will do? We will convert this in form of a real quantity, and the simple mathematical phenomena to convert this real quantity is taking its square. So, if we take that psi square, which is equivalent to psi multiplied by psi star, where the psi star is the conjugate, complex conjugate of this psi, then by doing some simple mathematics of this complex physics, complex mathematics, we will have this psi square is a real quantity. And the probability of experimental finding the body, this is described by the wave function at the position this x, y, z and the time t, and here, and this is proportional to the values of this psi square at that time t. And the what actually this psi square? This is the probability density, and it gives the existence of a particle of any specific position per unit volume, because the density term is here. And we know this, the large value of psi square means the strong possibility of the body of presence, while the small value of this psi square means the slight possibility of its presence. Now, this some more terminology we should know about this this matter wave, the phase velocity and group velocity. So, if you want to calculate this the velocity of that matter wave, then generally if you take that conventional mathematics, so far we are using to calculate that velocity for this progressive wave is given in terms of its frequency and lambda. So, this v is equivalent to nu multiplied by lambda, and when we put that frequency of this matter wave, that is equivalent to mc square by h, because h nu is equivalent to mc square. This is we can equate that that energy, photonic energy with energy mass equivalence, then we can get that frequency, and lambda is equivalent to h upon mb. So, we can take that relativistic term here, because this particular matter wave, it is good for atomic subatomic level particle, that is quantum mechanical particle. So, when we provide one small amount of energy to this, it actually goes in the region of that relativistic physics. So, in spite of taking that mass m as Newtonian mass or rest mass, we should take this as relativistic mass, and by doing some simple mathematics with this, we can get that the velocity, which is initially known as phase velocity, because it is related to the phase of that wave. That is why this is known as phase velocity, and this phase velocity is coming for this matter wave, it is equivalent to mc square by v. So, here that v is that velocity of that object, that body on which that matter wave is associated, and c is the speed of light. So, when we take that that object, it is the velocity of that object, it cannot be more than that speed of light. So, that v is much less than c. Then what we are getting, this phase velocity, it is actually being greater than the speed of light, and this is against Einstein physics, as well as this is also against the definition of matter wave, because in the definition of matter wave, this is a wave which is always associated with moving object. So, if the object's velocity is less than the speed of light and that matter wave's velocity is greater than the speed of light, then they cannot keep together, live together. So, that will be apart from that, that will be separated out. So, this is the against this the concept of that matter wave or the definition of matter wave also. That is why there is a need to search one a new expression or the new mathematics, new formula for the concept for the velocity of this matter wave. Then we have this the concept of group velocity, and this phase velocity is mathematically represented as omega by k, and this group velocity, this is represented as d omega by dk. And what is actually this group velocity? This group velocity is actually the velocity of wave packet. So, that wave packet, this is combination of waves. What actually that the theory behind this is, we take that big body, it is in part of that is small constituent particles, and it is considered that each constituent particles will contain one separate matter wave associated with that constituent particles, and since all these particles are compact, so there will be that superimposition of all these waves, and after that superimposition of these waves, one packet is formed, and that packet, which is actually the combination of so many waves, that is known as this the wave packet. So, the wave packet is the packet of wave, and these waves are actually the constituent waves related to the particles of that moving body. So, after some mathematics, one can get this the group velocity, it is equivalent to d omega by dk, and this can be proved this by doing mathematics. This group velocity is equivalent to the velocity of that object. So, the phase velocity that was greater than the speed of c, but here this group velocity of that matter wave means the velocity of matter wave, it is equivalent to the velocity of this body. It is mathematically proved. So, the shape of this wave packet actually depends on that constituent waves. If the constituent waves are random waves, then you can get one random wave type phenomena, where at the center there is a bump type structure, and other parameters are random one. So, there is one peak there at the center, and there may be, if all the waves are sinusoidal uniform type waves, then that the final wave in form of wave packet, that will be a good sinusoidal wave. So, here that wavelength is defined. So, here in the first case, if we think if we have a bump at the center, a narrow de Broglie wave group, this wave packet is also known as the wave group or de Broglie wave group. So, at the center there is one narrow de Broglie wave group. So, here if this is that the wave packet is actually the combination of wave, then we can ask that what is about that particle or the existence of particle inside this wave. So, in order to give the answer, we have to go for the mathematics behind that psi square. So, that psi square, which actually gives that probability of existence of any particle at a particular position at particular time. So, if this psi square is maximum, means at the that position where that the peak is maximum. So, if the peak is maximum, the probability of existence of that particle is maximum. So, this narrow de Broglie wave group here in this figure, the position of particle, this can be precisely determined, because there is one very narrow band. We can search that particle, we can get that particle. But here, because it is that just a disturbed wave, there is no proper wave shape. So, we cannot define its wavelength, we cannot get its wavelength. If we are not getting wavelength, then we have this formula P is equivalent to h upon lambda. So, we cannot get its momentum. So, in the first case, we can measure its position, but we cannot measure its momentum. But here, if we have that sinusoidal type wave where this wavelength is defined, but the peak value is uniform everywhere. So, that peak value is uniform everywhere means we cannot detect its position. So, in the second case where we have sinusoidal uniform wave type shape of this wave packet, we cannot precisely say about the position of that particle, but we can measure its wavelength, and accordingly we can measure its momentum. So, by this statement we can say that it is impossible to know both the exact position and exact momentum of the object at the same time, or we can say according to this is known as uncertainty principle given by Werner Heisenberg in 1927, that it is not possible to measure position and momentum of any atomic subatomic objects simultaneously as well as accurately. So, because in the first case where we are measuring its position, we are not able to measure its wavelength. In the second case where we are measuring its wavelength, we are not getting a momentum, we are not getting its position. So, simultaneously and accurately, if you want to measure its simultaneously, then accuracy, just forget about accuracy. If you want to measure accuracy, then you cannot measure it at the same time. So, this particular concept, this also differed this physics with our classical or Newtonian physics. In Newtonian physics, we have a set of equations which we are knowing as Newton's equations. So, in the first equation, B is equivalent to u plus at, you can get velocity, and accordingly you can calculate the momentum at time t if you are knowing about its acceleration, initial velocity, and at the same time you can measure its position, s is equivalent to ut plus half a t square. So, it is possible in classical physics that you can measure that momentum and position of accurately as well as simultaneously, but here this is not possible in for atomic subatomic level particle. But we want to measure that momentum and position at the same time. So, obviously there will be some error, and that error is known as uncertainty. So, uncertainty means the error, the percentage error. This is uncertainty, and it is denoted by delta x, and its a position, it is denoted by delta p, it is a momentum. And here we can deal with some simple mathematics related to that Gaussian formulation and other things, and we can derive this relation, but I am not going to the details of derivation of this relation, which is known as uncertainty relation, and I am just giving here the result. Actually, this calculation was performed by Max Born, because he was mathematician, and he had done this calculation for Heisenberg and gave this relation. So, according to this Heisenberg's relation, which was derived by Max Born, it is this delta x multiplied by delta p x, means we are thinking about that minimum error occurring in the simultaneous measurement. So, the multiplication of these errors in the position and multiplication of these errors in position and momentum, it is more than or equivalent to h upon 4 pi. Here this is delta x, this is error in position, which is known as uncertainty in the measurement of its position, and delta p, this is uncertainty in the measurement of its momentum. So, the multiplication of these two, it is greater than or equivalent to h upon 4 pi. So, minimum error at least will be there h upon 4 pi, and this relation, what we are observing, this relation is the multiplication of two quantum parameters, delta x and delta p, and that output, that is one real quantity, means this delta x and delta p, the multiplication of these two is a real one, means these are complex conjugate. So, it was further calculated for some more complex conjugate materials, or one can say some relations are derived by using this. So, this some more relations, that is delta t multiplied by delta e, it is greater than or equivalent to h upon 4 pi. So, here this delta t will be definitely the uncertainty in its time, and delta e, that will be uncertainty in its energy. There is some one set of relation, that is delta theta multiplied by delta j, it is greater than or equivalent to h upon 4 pi. Here delta t, that is the uncertainty in the measurement of angular position, delta j, that will be uncertainty in the position of angular momentum. So, these are the set of equations which are known as uncertainty relation. So, here we use h cross or h bar in quantum physics. H bar is equivalent to h upon 2 pi, which is equivalent to 1.05 into 10 to minus 34 joule second, and first time this is used by Niels Bohr when he was giving that the quantization of that angular momentum. So, this was the first time used by him, and here we can use this. So, in a standard book, that relation is given as delta x multiplied by delta p, it is greater than or equivalent to h cross by 2. So, in spite of h upon 4 pi, one can use this h cross by 2. Some thought experiments are there to support this uncertainty relation, and there are two sets of thought experiments. One is that gamma rays microscope, and second one is that electron diffraction. That electron, it is initially it was initially considered as a particle, but after de Broglie's hypothesis we have shown that this electron will have the wave nature. If it has wave nature, and obviously it will show that diffraction. So, this diffraction phenomena, it is used to measure this the wavelength of electron by Davies and Germer, and as I have mentioned as J.P. Thomson, but this diffraction can be observed in the slit, similar to that that X-ray diffraction or that the diffraction of light. And here by using simple mathematics, first one is that gamma rays microscopy, and we know about that mechanism or the function of one microscope. If there is some object and that light incident on that object, then after reflection that reflecting light is captured by that eyepiece of that microscope. So, here also one thought experiment is designed for this gamma rays microscope, where in spite of that light rays, so gamma rays are incident on that vibrating atom. So, that vibrating atom means its a position, there is uncertainty in the position, it is vibrating, it is not fixed. So, uncertainty in the position, that is delta x, and this delta x, it is detected, it will be detected only when if uncertainty in the position, that will be equivalent to the resolving power of that microscope. So, that resolving power of that microscope is generally shown as lambda upon sin theta. If this theta is the half angle of that lens used in that eyepiece. So, this delta x can be mathematically written as equivalent to limit. So, the mechanism is that gamma rays along x axis, it went to that oscillating atoms and it collides them, and then it reflects to that eye lens of that microscope, and there is uncertainty in the direction of reflection, because it can go to that one specific the direction, but that direction must be in the range of that eye lens. So, that the uncertainty in the momentum, it was calculated mathematically by that, and by giving the multiplication terms this delta x and delta p, one can get the value that is equivalent to h upon 2. So, this is one thought experiment, and this is in the support of that de Broglie's relation. Some applications, and as I have mentioned that it has the applications to discuss about some complex physical phenomena. So, I am giving two statements related to different part of physics. One is related to that emission of beta rays, and second one is related to the structure of atom. So, in the concept of that beta rays are the emission of that beta rays, these are actually that nuclear phenomena. So, in the nucleus we are getting that alpha particles, beta particles, gamma rays, and out of these three, that beta particles are electrons. So, this is the concept that electrons are coming out from the nucleus. Whereas, in the second part, when we think about that structure of atom, so this is made up of nucleus and electrons moving around that. So, in the nucleus, protons and neutrons are there is no electrons at all, and electrons are moving around that nucleus. So, in the first statement, electrons are coming out from the center, and the second statement that electrons cannot exist inside the nucleus. So, by using this Heisenberg's uncertainty relation, we can prove electron cannot exist inside that nucleus, and for which we can take one atomic nucleus, and generally that atomic nucleus size is equivalent to about 5 Fermi, and this is that is smallest unit. So, this 5 Fermi is 5 into 10 to the minus 15 meters in the radius. And let us assume that one electron is inside that nucleus, means that the uncertainty in the position of that electron, that will be equivalent to the diameter of that nucleus. So, that will be 2 times this 5 into 10 to the power minus 15 meter. So, this will be that delta x, that is uncertainty in the position. We can calculate that momentum. So, that momentum is equivalent to, by using that Heisenberg's uncertainty relation, we have this delta x multiplied by delta p, that is equivalent to h cross by 2, where h cross is equivalent to 1.05 into 10 to the minus 34 joules second. So, by using this relation, we can calculate delta p, and this delta p, after calculating this delta p, we can calculate energy. And since, as I have mentioned, that electrons can be considered as a relativistic particle. So, we can use the relativistic relation for the calculation of energy. So, this delta E is equivalent to delta P multiplied by C. So, by putting the value of that P and C, we can get that energy that is about that will be in the range of 10 to 12 electron mega electron volt. So, this is one huge amount of energy, and maximum energy that is we can calculate depending on that size of nucleus, it is about 20 mega electrons. But what that experimental evidence related to that beta particle says, that beta particles energy, it is actually in the range of 2 to 3 electron volt. And if we are assuming that there is one free electrons inside that nucleus, then that energy is coming in the range of that 10 to 12 mega electron volts. So, one cannot compare the energy of this beta particles with that free electrons, means we can say there is no existence of that free electrons inside the nucleus, and these beta particles are actually the result of some nuclear phenomena, and this nuclear phenomena that was explained by Moseley, that is related to that proton neutron interconversion theory. Okay, so, this is one of the method, the mystery which is solved by Heisenberg's uncertainty relation. Second, we can calculate the binding energy of any electron in the atom, especially here I am giving that example of hydrogen. So, we know that the diameter of first Bohr orbit that is actually equal to the radius of first Bohr orbit, that is equivalent to 0.529 angstrom. So, the diameter of that orbit will be the double of this. So, if we are thinking about that electrons orbiting around that first Bohr orbit, then it is uncertain in the position, that will be the double of this radius of this, and we can calculate its momentum by using obviously that momentum multiplied by delta x multiplied by delta p is equivalent to h upon h cross by 2, and so we can get that momentum, and finally we will have that energy, and that energy, it is the that will be the binding energy of that electron. So, the binding energy of that electron, this can be calculated by using this Heisenberg's uncertainty relation also. So, this is also one of good application of Heisenberg's uncertainty relation. Next one is we have the concept related to laser, where we consider there are different energy levels, and we think about different types of transition. So, from ground state, one electron is moving from ground state to higher energy state by using absorption transition, and then that atom is coming back to the ground state by emitting that photon. And there we are thinking about at the higher energy level, that is known as excited energy levels, that lifetime we in general mentioned at 10 to the minus 8 second. And from here this lifetime this is coming from. It is actually that mathematics we performed using this Heisenberg's uncertainty relation, and we have this energy time relation. So, delta T multiplied by delta E, it is equivalent to h cross by 2. So, if we have the difference between two levels in the ground state and that excited state level, that delta E, if you are having the data, if let us say it is about 20 electron volt, then by putting that value in this relation, this delta T, it is equivalent to h cross by 2 multiplied by delta E, we can get that delta T. This delta T is this the lifetime of any type of this transition, which is actually that quantum mechanical phenomena. So, in that luminescence type materials, or that laser technology or laser mechanism, whenever we are using this the concept of this lifetime, it can be actually calculated by using this Heisenberg's energy time relation. Now, let us conclude the lecture. So, in order to understand this Heisenberg's uncertainty relation, we initially dealt with the concept of this matter wave, which is a wave which always associated with a moving object, and we have initially its wavelength, that is equivalent to h upon p, and by doing some mathematics for different types of objects, we have different formula for the de Broglie's wavelength, and mathematically we can calculate that wavelength of matter wave associated with the second. So, this was the first thing we should know about the concept of this matter wave, or that the wave nature of particle. Second, we have interpreted it is a wave function, because this wave function actually gives the probability of existence of any particle. And here, since in the Heisenberg's uncertainty principle, we are thinking about that position of any atomic subatomic level particle, means we should know about its position. So, its position, it is shown by the probability of existence of that particle, which is represented by the square of this wave function psi. So, that is why we have included that term related to wave function psi, which is basically given by Max Born, and it is a physical interpretation in terms of this probability density psi square. So, this psi square, this gives the probability density of that particle at position x y z at time t. So, this is that real quantity, and then we move to its velocity also, because we should have to the concept of wave packet, because we are trying to search the position. So, we have the concept of wave packet, we have the concept of drift velocity, we have concept of phase velocity, group velocity, and this group velocity is actually the velocity of matter wave. And for this group velocity, we are using that the concept of wave packet. This is the packet of waves, and in this packet of wave, we are trying to search that particle, and we are getting that if that this wave packet is narrow enough, we can get its position. So, but its the wavelength or momentum we cannot get accurately, and here if we have a broad packet of wave, that is the wave packet, there that wavelength is properly defined, then we can get momentum, and its position cannot be measured. So, in a single sentence we can say it is impossible to carry out the measurement of position and momentum of any atomic subatomic. This term should be used, atomic subatomic, because this is quantum mechanical phenomena simultaneously and accurately. And then we have three types of that Heisenberg's uncertainty relation. One is related to linear momentum and linear position, second is related to time and that energy, and third one is related to angular momentum and angular position, and the multiplication of these uncertainties on this conjugate parameters, uncertainties on these conjugate parameters are greater than or equivalent to h cross by 2, where h cross this is h upon 2 pi. And then we have discussed about some thought experiments, and especially I have given the example of one thought experiment, that is the gamma rays microscope, and then we tried to give that applications of this Heisenberg's uncertainty relation. One is related to that the electron cannot exist inside the nucleus, second is related to that binding energy of electrons moving in the orbital, and the third one is that is related to that time taken by any electron to transfer from one energy level to another energy level, depending on the gap of that energy levels. So, these are the terms we have discussed, the concept we have discussed in this particular lecture. Thank you all, enjoy learning.